Hello everyone, we've just talked about the problem minimum height trees. So if you're unfamiliar with the problem, either try to solve it yourself or watch my previous video from today, where we talked about this problem, about the observations necessary to solve it, and we've shown probably the simplest solution, which is the result of all those observations. So we talked over this solution, which is probably intended. However, my first idea when I saw this problem, and perhaps one that requires fewer observations, but also requires a bit less of a trivial algorithm, is a solution based on tree diameter. Because notice that, as we utilizing some of the knowledge that we've talked about previously, when we find the tree diameter, we find two nodes such that the distance between them is the largest such distance possible within the tree. Then we can find our center nodes, our candidates, by just looking at their distances from those ends. So we can go through all of our nodes right now, look at their distances. So we're interested both in the maximum distance between those two, and are also interested in the balance between the distance from one end and from another end. So essentially, we want this balance to be as balanced as possible. As we talked about, that's what the center node would be. So it's best if those distances are equal. If those distances are not equal, then they may differ by one, but it would be better if they were equal, because those are those two cases where we have either two answers or one answer. And we also want to break ties by the maximum distance between, because it was actually one of those examples where we have a node that's at the center, and this is the answer. This center node is the answer, and it has, if those are, let's say, the two nodes that we have found on the diameter, so this one and this one, then it is perfectly balanced. So the absolute value of the difference between those two distances is 0, and the maximum is 1. And for this node, the absolute value of the difference is also 0, but those distances are 2, so this is not a correct node. We have to also minimize that maximum distance. And then we just remember all the nodes that do it. So the only problem is how to find those two nodes that are the end of a diameter. And this is actually a pretty funny idea if you haven't seen it before. Here, of course, we just read in the graph. And the idea is just that the tree diameter can be found by starting from, this is just a normal DFS, and we run this DFS calculating distances from nodes. We start at any node, then we find the furthest node from it, and then we find the furthest node from that node, and this is a diameter. Probably the easiest way to think about it, and I encourage you to think about it if you haven't already, is to now look at this tree as starting on one end, ending at the other end, and there can be some legs coming out of this caterpillar, short legs, long legs, and the central idea is that when you look at this point where a leg comes out of the caterpillar, then this distance cannot be greater than this distance, because otherwise this would be a longer diameter. So essentially, that's the funny algorithm for finding the tree diameter, and also that calculates for every vertex the distance to one end and the distance to the other end. And when we have those values, then we can solve our problem using them as we talked previously.